Hi, Dr. P here, and in this lecture we're going to look at another type of nucleophile. It's essentially a carbon nucleophile, but it also makes use of phosphorus. So actually the phosphorus is doing, it's kind of activating the carbon, if you will, and it's called the Wittig reaction. So that's what the German pronunciation, Wittig. So let's go ahead and let me show you what the Wittig reaction is. So we'll start with this kind of funky compound that has a phosphorus and 3 phenyl groups, so big benzene rings, and then carbon, hydrogen, and some kind of R group, and then we're going to have a lone pair, and we have a negative charge on the carbon, positive charge on the phosphorus. Now, this has a resonance structure that is not charged, and even the molecule that has individual charges is net neutral. And this type of molecule is called an ylide. If I could spell it correctly, Y-L-I-D-E. It's pronounced ylide. And the ylide refers to having both a positive and negative charge right next to each other. So we have this ylide, and then it's going to react with an aldehyde or ketone, and we're going to get, so let's do R prime carbon, R double prime double bond O, plus PH3P CHR, negative charge, positive charge. And so what we're going to get is we'll see that we'll essentially get this, or not essentially, we will get this phosphorus-carbon bond cleaving, and we'll also get this carbon-oxygen bond cleaving. And so we'll take the carbon of the aldehyde or ketone and its substituents, and then we'll connect that to the carbon in the ylide with its substituents. So this is going to look like RCR. Put the primes on there. Double bond CRH. And you can get a mixture of isomers. So if R prime and R double prime are different things, I forget, and I'm not going to hold you responsible for which side is more likely to have the hydrogen. This is actually a good way to make di-substituted and tri-substituted alkenes. Typically, we're not going to use a di-substituted ylide here for steric reasons. Okay, so good way to make di and tri-substituted alkenes. And we'll say tetrasubstituted to hindered. Okay. The other, our byproduct here is PH3P double bond O, a triphenyl phosphate, or rather triphenyl phosphine oxide, and that's a byproduct. We'll get rid of that. So this is a kind of sort of elegant way. I thought it was kind of cool the first time I saw it, but a kind of a nice way of making carbon-carbon bonds. Okay, and you know, organic chemists are really kind of all about making carbon-carbon bonds because that's how you build up more complex molecules from simpler ones. Let's take a look at the mechanism for this reaction. Okay, so we're going to start with our aldehyde or ketone here. So R prime, R double prime. And we'll have our ylid, PH3P, C, positive charge on the phosphorus, H, R there, negative charge on the carbon. And we'll go ahead and we will get attack on the carbonyl carbon, of course, because that is electron deficient, and we essentially have a carbanion here, or it kind of functions like one. And so that now gives us, let's see, I'll have R prime C, R double prime O. I'm just going to twist this around a little bit because I want to get it to line up a particular way to show you how the next step kind of naturally occurs. And then I've got my phosphorus with pH, pH, pH. There we go. And that guy still has a positive charge on it, because phosphorus with 4 bonds on it would have a positive charge, just like nitrogen with 4 bonds. And this is referred to as a beta-ene. I'll just write it in blue here. You don't really need to know these. But it's the particular type of intermediate. Now the negative charge from the oxygen can come to make a bond with the phosphorus. So that gives us this intermediate here. And now with 5 bonds on phosphorus, it's neutral. And this is an oxophosphitene intermediate. So if you see these words being used, you understand what they are. And now, this is never isolated. Instead, it collapses. And we have those electrons going there to make a new CC double bond. And the electrons from the carbon-oxygen bond go to make a PO double bond. And so we end up with C, R prime, R double bond, C, H, R, plus P double bond O, PH, PH, PH. And there we go. So it all starts with a nucleophilic attack, just like the other reactions we've seen in this chapter. Now, I'm actually not going to quiz you on this, but I do want you to understand how it works. You may, however, need to use the Wittig in synthesis. And of course, you will have to predict products and stuff. One thing that I should mention is, in order to make the ylid, you have to do the following. We're going to take triphenylphosphine, PH3P, so it's a phosphorus with 3 benzene rings attached to it. And we'll use it to do, so let me just draw it out here for you guys. And a lone pair. So now this can be a reasonable nucleophile and can do an SN2 reaction. So we could have something like, let's do RCH2I, and then we'll treat it with butyl lithium or another strong base, and that's going to deprotonate. So we'll get PH3P, CH, R, and then the butyl lithium takes off one of those hydrogens. So phosphorus attacks the carbon, or the iodine's attached, kicks off the iodine, SN2. Butyl lithium comes along, pulls off that other hydrogen, and so now we've got our ylid. And you could always draw it as, again, or we could draw it as PH3P double bond CHR. You can always draw it like that because that is a resonance structure. So let's look at a couple of examples here. Okay, let's look at a couple of examples here. Okay, so let's say we had the following. We have cyclohexanone, and we treat this with PH3P double bond CH2. What do we get? Well, the way to answer this is to remember is to recognize, first of all, that you have a Wittig. So when you see the PH3P, that should be a giveaway. We have a Wittig. So what I'm going to do is I'm going to cleave this bond and I'm going to cleave that bond. And then I'm going to stick my CH2 to the carbon part from my ketone. So I could just go ahead and draw in. So there's the carbon part of my ketone, and now I'm going to have CH2 here. So CH. And the text actually makes a point of mentioning that this is actually a pretty good way of making just this guy. So let me just show you that particular figure from the text here. So let me zoom in slightly here. Remember back in 12A when we looked at making double bonds, if we had an OH, an alcohol present, we could do a dehydration. So one technique to try to get this product from cyclohexanone would be to do a Grignard. So that would give us this guy with the OH and the methyl group. And then we dehydrate. The only problem is we mostly get this guy because it's more stable than that guy. Now I could try to use something like, I don't know, PBr3 to swap it out, but that's tertiary, so it doesn't work too well. You know, I could try to, get around that, or I could do a Wittig, because the Wittig will only give us this product. We won't get any of this guy because we can't get the reaction there. It's just between this carbon and that carbon there. So I thought that was kind of cool, the way that the text mentioned that. All right, let me zoom back out here. Whoops, too much. One more. There we go. I think that should be good there. Check my. Yeah, that's okay. I think that should be good. So the other example I had. Let's say we had something asymmetric, and we treated that with PH3P double bond CH3. So now, of course, this guy is PH3PC, positive charge there, H and CH3, like that, with negative charge. So in this case, we actually can get a mixture of E and Z products. So, we'll break those and we'll attach this part to that part. And so I could have 1, 2, 3, 4, C double bond H CH3 plus 1, 2, 3, 4 double bond C H CH3. And I don't remember the exact product, or I actually don't remember the product ratio of these at all. I'm actually inclined to say that you might expect the hydrogen to be cis to the larger group here, but I don't think that's the case. So it's a little funky. So you might hear that. I believe somebody is approaching the door. So why don't I end the lecture on that note? My dog barking. And anyway, this was the Wittig reaction. And maybe I'll talk about the use of it in synthesis in class in our in-person meeting. All right. The next lecture should be the last lecture for this chapter, and that's looking at conjugate addition, and which we'll get into in more detail in a later chapter, but I want to introduce it now. All right, well, until next time, stay safe out there. Bye now.